In this video, we're going to go over how glycogen metabolism is controlled. Now, as we saw in our previous videos where we looked at glycogen synthesis and breakdown, if we allow both of those cycles to go, the only thing that would happen is that we're going to waste UTP, which means we are wasting ATP. So we need to control metabolism so we're not doing synthesis and breakdown at the same time. The way we do that is allosteric controls and hormonal controls. Glycogen phosphorylase and glycogen synthase are going to be our main targets, and ATP, G6P, and AMP are going to be our allosteric regulators. Just for an example how this works, when demand for ATP is high, which means in your cell you have low ATP concentration, low glucose 6-phosphate concentration, and high AMP concentration, glycogen phosphorylase is going to be stimulated and you're going to stop making glycogen because you need energy, so don't store glucose away. Break up glucose from glycogen. While if you have a lot of ATP and glucose 6-phosphate in your cell, start making glycogen. Start storing this glucose. We have enough energy. Don't break down more glucose. We don't need it. We can do some more control on our enzymes via phosphorylation and dephosphorylation. All right, so let's take a look at these schemes, and this is what's called an enzyme system or enzymatically interconvertible enzyme system. Just means we have a lot of enzymes that are all connected, and this phosphorylation event is reversible, interconvertible, right? And this just allows us to have much finer control over our whole system. All these levers and all these dials are allowing us to finely tune how much glycogen we're either breaking down or creating. And it allows for simple signal amplification. So if you get a signal like AMP, this can be amplified through many stages, so you can have a big effect from just a small change in the AMP concentration in your cell. The three enzymes we're going to be looking at are phosphorylkinase, shown right here. Phosphorylkinase will phosphorylate serine 14 of glycogen phosphorylase B. So phosphorylase kinase turns on glycogen phosphorylase and turns into the A form. We also have PKA, or protein kinase A. PKA will phosphorylase kinase. So PKA turns on phosphorylase kinase. Phosphorylase kinase turns on glycogen phosphorylase. And these two can be shut off through the enzyme phosphoprotein phosphatase 1. Horrible name, so we're going to call it PP1. PP1 will dephosphorylase glycogen phosphorylase and phosphorylase kinase. So this is turning off, this is turning on. So every time we see one of these pictures, green means more active, red means less active. And this whole scheme can be turned on through cyclic AMP. Remember, cyclic AMP means we're low in energy, we need ATP, turn on protein kinase A, which will go and turn on phosphorylase kinase, which will go and turn on glycogen phosphorylase, which will break down our glycogen into glucose. And so this is an amplification scheme. Let's say we turn on 10 protein kinases with our CMP. Those 10 protein kinases can turn on 100 phosphorylase kinase. These 100 phosphorylase kinase can turn on, let's say, 100 glycogen phosphorylase. So you can see how large of a signal amplification we can actually get through a scheme like this. All right, so we're going to look at phosphorylase kinase to begin with. 1300 kilodalton protein has 4 subunits, all different. We call them alpha, beta, gamma, and delta. Gamma is where the catalytic it's the catalytic subunit. It's where the active site is. And this will be turned on all the way if you have calcium around and if alpha and beta subunits are phosphorylated by protein kinase A. So alpha and B gets phosphorylated and you have calcium around, this thing is going to be on. Now, this protein can inhibit itself, and it does it by the C-terminus. So the C-terminus will go and bind to its own active site, unless alpha and beta subunits are phosphorylated. So that's why I'm saying here, alpha and beta subunits turn on this enzyme, because it's actually blocking the C-terminus of itself from binding in the active site. So it's blocking the C-terminus, allowing the active site to be open, allowing for phosphorylations to happen. Now this delta subunit is called calmodulin. Calmodulin is actually a just common protein in your cell. It's not just found here. It can be found by itself, or it can be found in other proteins. And calmodulin binds calcium. That's what calmodulin does. And when you bind calcium, you also get a change in your conformation, which can no longer have your C-terminus blocking your active site. You stop this autoinhibition. Now, what's interesting is if you remember from Biochem 1, we talked about muscle contractions. And we said one of the first things you need to happen for muscle contractions to work is a release of calcium. Calcium will bind troponin and tropomyosin, and it'll release troponin and tropomyosin that was surrounding your actin. Now your myosin head can bind to your actin. Well, this also works with calcium. So when you want to move your muscles, you release calcium, which allows your myosin to bind to your actin. You get the power stroke. This also turns on phosphorylase kinase, which will go and phosphorylate other enzymes to break down glycogen, giving you glucose, giving you ATP. So you can see all of our systems are interconnected, and that's why it's so hard to actually understand how the body works, because everything just seems to be interconnected. All right, so how is PP1 regulated? So PP1, if you remember, that is the enzyme that is turning off phosphorylase kinase, and it's turning off glycogen phosphorylase. And so PP1 is removing phosphoryl groups from these enzymes. And the control mechanism is different depending on if we're talking muscle or liver. We're going to start with the muscle first. So the catalytic subunit of PP1 is called PPC, shown here. PPC is only active when it is bound to glycogen. And it binds to glycogen through its subunit we call GM, glycogen binding subunit muscle, so GM. So GM is part of PP1. PP1C is the catalytic subunit, and that's really only activated when it's bound to glycogen. All right, so PP1C, the activity of it, and the affinity of GM to glycogen, or its affinity to GM, it's regulated by phosphorylation. And the phosphorylation is on this GM subunit. Remember, it's the glycogen binding subunit. And GM has two sites. So we're going to start at the top here. Site 1 gets phosphorylated through insulin. So when you release insulin, one of the many things it does is it's going to turn on some protein kinase. This protein kinase, it's going to use ATP, and it's going to phosphorylate this GM subunit. When this GM subunit is phosphorylated in site 1, PP1C is turned on. When PP1C is turned on, it will go and remove the phosphates from phosphorylase kinase and glycogen phosphorylase. When it does that, you're stopping the breakdown of glycogen, and rather you're allowing glycogen synthesis to happen, which should make total sense, right? Insulin is released when you have high blood glucose levels. If you have high blood glucose levels, don't break down your storage of glucose. We have enough glucose, so stop breaking it down. The way we stop breaking it down is by removing these phosphates. Now, site 2 of GM can be phosphorylated by PKA, right? So protein kinase A, which starts our whole cascade here, can be turned on by many things. One of those can be epinephrine. So epinephrine can turn on protein kinase A. Protein kinase A can go and phosphorylate site 2. It can also phosphorylate site 1 as well. So when PKA phosphorylates site 2, what happens is that the PP1C, the catalytic unit of PP1, is removed from the GM subunit. The PP1C goes off into the cytoplasm. In the cytoplasm, it can also bind something else to be further inhibited. So this PP1C is no longer working. Since this PP1C is no longer working, phosphorylase kinase will become phosphorylated, glycogen phosphorylase will become activated, break down glycogen. Also, you are activating protein kinase A. And it makes sense. We'll talk about it a little bit later, but epinephrine is one of your fight or flight hormones. So you're getting ready for action. So you want ATP around. So you want to start breaking down that glycogen to get ATP from glucose. All right, so we can look at a big map of this and really just realize our whole system, as I alluded to earlier in the video, it can be directly related to the concentration of cyclic AMP. So cyclic AMP means we're low in energy. So what cyclic AMP does is that it'll turn on protein kinase A here in the top. Protein kinase A will then go, if you want to follow this gold line, it will turn on phosphorylase kinase A. Phosphorylase kinase A will go and turn on glycogen phosphorylase A, which means we're breaking down glucose, which is good because cyclic AMP means we need energy. It will go and shut off glycogen synthase, which is good. Glycogen synthase creates glucose, or glycogen rather. We don't need to store glucose if we're low in energy. We need to break it down. PKA will also go and turn on phosphoprotein phosphatase inhibitor 1A, which we just talked about will inhibit PP1C. So if you inhibit PP1C, you're allowing glycogen to break down again. And if you're allowing glycogen to break down, that means you're getting energy. Now that was all muscle. Let's just briefly look at liver PP1. And the glycogen binding unit here is GL, not GM, as we saw in the muscle. Here, we're not dealing with phosphorylation as we did in the muscle. Rather, activation or activity rather of PP1 is directly controlled by binding to phosphorylase A. Remember, phosphorylase A can break down glycogen, right? And PP1 will dephosphorylate this and form it into the T form. Now, PP1 will bind to phosphorylase A both in the R form and the T form. So it will bind to the R form. So R form binds to PP1. When you get an R to T transition, which happens when you have a lot of glucose. So you have a lot of glucose, so stop breaking down glycogen. Phosphorylase A goes into the T form. And something very cool happens when that occurs. PP1 is the enzyme that is bound here and will chop off your phosphates. So your phosphates are now chopped off. Now you're in phosphorylase B and you are in the inactive form. When you're in phosphorylase B, PP1 can fly off and can start dephosphorylating other things like phosphorylase kinase to stop the breakdown of glycogen. Because if you have a lot of glucose, don't break down glycogen. Now in the liver, since you have so much glycogen, this will only happen if 90% of your phosphorylases are in B. So you have to have a lot of glucose around until you're going to stop breaking down glycogen in the liver. So as we saw, As I just said, this is just a repeat of what I just said. Glucose is high, phosphorylase A to the T state, then you're controlling glycogen metabolism in the liver. So I know that was a lot of charts there, but I want you to sit down, look at the logic, and try not to get confused with all the names of the enzymes. Write down, like I did in the slide, what do they do? Do they break down glycogen? Do they synthesize glycogen? What are they turned on by? Cyclic AMP, what does that mean? Once you start making lists like that in your head, those charts of all those enzymes become a little less intimidating, because it's really, at the end of the day, it's logic. You need energy? Well, break down glycogen. You don't need energy? Make glycogen. Alright, and that's it for this video. I will see you in the next one.